Let's talk about gases. Uh, okay, what I meant was let's talk about rules about gases.
Or sneeze or burp or fart.
All right, let me rephrase that. Let's talk about gas laws, which are mathematical relationships that describe the properties and more behaviors of gases. How about that? Those kinds of gas laws. All right, let's talk that. So where do we start? We need to remember, and you already have this because we talked about it in class, and you don't need to write this down, but we need to remember that the main properties of gases that set them apart and give them different relationships, different rules, are that they are easy to compress. So I can take a large amount of gas and I can squish it into a smaller space. They also expand to fill their container. Liquids take the shape of their container. Gases will take the volume of the container. So if I put a tiny amount of gas into a large container, it's still going to fill that container. And then lastly, they're going to occupy far more space than the solid or liquid form. So a few particles of gas use a lot of space compared to, say, the same number of particles of a liquid or a solid. And if you think about it just for a second, if you've ever watched water boil, not the most fun, but if you watch water boil, you look at the bottom of the pan and all of a sudden you can get these great big bubbles of gas, water vapor, but the volume of the pot doesn't really drop all that fast. Yeah, it's true, if you let the water boil, it's going to get smaller, 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 but you get these big bubbles of water vapor, water gas coming out. And that's because water gas, takes up a lot more space than the same mass of water as a liquid. So we're going to start with something called Boyle's Law. Boyle's Law is named after Robert Boyle. And there's Robert Boyle. And he lived a long time ago. We don't really need to know when he lived. We don't really need to know his first name. What we do want to know is that Boyle's Law tells us about the volume and pressure at constant temperature. In other words, how did the volume and the pressure change if we're not paying any attention to the temperature? And it's an inverse relationship. And what that means is as one increases, the other one decreases. As one goes up, the other one goes down. So if you think about a syringe, and I don't know how well you can see this, but if you think about a syringe, if I plug that hole, if I squish it, right, I add pressure, I increase the pressure on that syringe, the volume goes down. Mathematically, and you don't need to write this part down, mathematically I can express that relationship in this form. So I've got a volume, and that symbol here is a mathematical symbol that means proportional to, or changes as. So the volume changes with the inverse of pressure. So if this one goes up, that one's going to go down. However, we don't want that. We can't really do a lot with that mathematically. This is one form of Boyle's Law. Again, we don't need to write this one down because it's not the form we're going to use, but really what's happened here is I've removed that proportional symbol with an equal sign and a constant. In other words, if I were to cut the pressure, so if I were to double the pressure, I would cut the volume in half. That kind of linear relationship. So now I can make it look a little bit more like a linear equation using this. What we really want is this form of Boyle's Law, because really what we're always going to be wanting to know is if I start with this volume and this pressure and I change something, change the volume, change the pressure, how will the other one respond? So I'm always looking at a before-after kind of picture. So that one's important. Charles' Law is another one. Now Charles was a Frenchman, Jacques Charles, lived a little bit later than Boyle. Again, we don't need to, he lived in France, so he looks French. We don't need to know the date, we don't need to know the first name. What we need to know is that Charles' Law is looking at volume and temperature at constant pressure. And that's a direct relationship. So as I increase the temperature, I will increase the volume. Now we already know this because we know that as you increase the temperature, heat things up, they tend to expand, they tend to get bigger. And gases are going to respond to that increase in temperature much more quickly and to a much greater extent than liquids or solids do. But the same kind of pattern. Cool it down, they get smaller. Heat it up, they get larger. The particles don't get larger, but the amount of volume that all those particles occupy gets larger. So doing the same kind of proportional symbol, same kind of math, we're going to go through the same kind of process. So I would say write a direct relationship in this form, so that the volume changes with temperature directly. Temperature goes up, volume goes up. Get rid of the proportional symbol and make it more look like a linear equation, and it looks something like that. But the real form of Charles' law is either of these. Now, one is just the reciprocal of the other. So I don't really need to write down both. I already did. You don't really need to write down both. Just understand that if I have volumes on the tops of both or temperatures on the tops of both, it works either way. Once in a while, it's more convenient to solve for volume on top. Sometimes I'm solving for temperature, so I want it on top. But that's about the only difference between the two. Third one is Guy-Lussac's law. And Guy-Lussac, another Frenchman. Now, I have debated. It's not the timing that's debated. It's not even his name that's debated. It's whether or not he really discovered the law. So I'm often going to refer to this. So there's Guy-Lussac, if it was him, is I'm just going to call it the pressure-temperature law. In other words, how does temperature and pressure change? How does one change as the other one changes? And it's also a direct relationship. Now, this is your metal can, your aerosol can in the fire question, right? Or as some people call it, redneck fireworks. And we know it's a direct relationship. If I increase the temperature, then I will increase the pressure. And aerosol cans come with that warning. Don't store this thing in a hot area. Keep it out of direct sunlight and all kinds of other things. There's rules about if you're carrying around a propane tank in the back of your car, what you're supposed to do with that and laws like that. And the reason is temperature goes up, pressure goes up. We don't need to know the proportional part. We really even don't need to know the linear relationship part. What we need to know is Guy-Lussac's law or the pressure temperature law in one form or the other. And again, same as Charles' law, one is just the reciprocal of the other. Please understand that the forms of the rules, right, whether I've got a fraction or whether I've got a V1, P1, V2, P2, like in Boyle's law, matters. And if I were to come up with some other kind of ratio, I might end up doing something incorrect. And it really comes down to the fact of whether or not it's a direct relationship or an inverse relationship. There is, however, a problem. And the problem is very simple. And if you were to start to think about these two, so we've got Charles' law and I've got Guy-Lussac's law, what would happen if I use this formula on a cold day, if the temperature was 0 degrees Celsius? Well, if I think about this mathematically, if I put a 0 in here, I've got a 0 volume or 0 pressure. Well, what if it were minus 10? Well, throwing a negative number in for temperature, I'm going to end up with negative volumes and negative pressures. Particularly a negative volume doesn't really make a lot of sense. The other thing is, what if you went down to the States? What do they do? What is Boyle's law or Charles' law? How does that function? Sorry, this is Guy-Lussac's law. How does that function in the United States where they're using Fahrenheit scale? So now if I'm at, well, even let's pick a 20 degrees, that's 60 something, almost 70 something in the United States. What do I do there? Well, the answer to the problem is very simple. I have to use a different temperature scale. I have to use a temperature scale that works over all things. The Kelvin scale is a bit different. The Kelvin scale is sometimes called the absolute scale. And the bottom line with it is 0 Kelvin is the lowest possible temperature you can get. You cannot have negative temperatures on the Kelvin scale. And we call it absolute 0. And you'll see that over here. And the absolute scale, or the Kelvin scale, is based on molecular motion. We know that as you cool things down, the particles move slower. As you heat them up, they move faster. Well, if I keep cooling them down, cool them down, cool them down, eventually I'm going to slow them down, stop. That is 0 Kelvin. So we talk about absolute 0, all molecular motion stops. That's all interesting. We don't need to write it down. Sorry if you already did. What's important for us is this part, that to convert from Celsius to Kelvin, I add 273. And that is, if you look at 0 Celsius, that's, I don't know, it says 273.15. We'll ignore the 0.15 and we'll add 273. All right, so now what do I do? Now I've got Boyle's law, Charles' law, Guy-Lussac's law, or the pressure temperature law, and a way to get a proper temperature. Now here's the thing. For these temperatures, I will only give you Celsius temperatures because that's what we measure. I've never seen a Kelvin thermometer. Your job will be to take the Celsius temperature, convert it to Kelvin. There's one more thing, and it's not a change, it's just that as we start to work with gases in different places in the world, we want to kind of talk about the same stuff. So we end up with a set of conditions called SATP, and that stands for Standard Ambient, which means room, normal, Standard Ambient Temperature and Pressure. And it's just a set of conditions that have been defined, and that's 100 kilopascals and 25 degrees Celsius, which of course means when we use this, it's 100 kilopascals, pascals, and 298 Kelvin. So that is a set of conditions that we're going to need to know. So here are the 1, 2, 3, 4, 5 things that we need to know. The 3 laws that carry a name, how to get the proper temperature, and that set of conditions, standard ambient temperature and pressure. What do we do with them? Well, we're going to use them in questions. So I'm going to give you some questions. Here's a typical kind of question. And when you get that kind of question, part of your job is to look at it and say, okay, I've got a volume at first. I've got a pressure at first. And then things are changing, and I'm trying to find a new volume at this new pressure. Oh, hey, look at this. I've got a volume, a pressure, and another pressure, and I'm looking for the second pressure. Looks like I'm doing a Boyle's law. So that's the kind of thing you're going to have to be able to do with it. So you're going to use Boyle's law, and you're going to calculate that out. Now, I'm going to let you to do that, and then I've got, I think the answers are showing up in a couple of minutes. Or a question will be, a gas occupies this volume, so that's a volume, at 15 degrees Celsius. So that's kind of the first temperature, right? We have to convert to Kelvin. Calculate the new volume, second volume, at this new temperature. And again, it's in quotation marks because I can't use 15, I can't use 120. Well, I can, I just get the wrong answer. And so then I'm using Charles' law, and I have to convert my temperatures. And then finally, not finally, but additionally, I've got a gas and metal container. Now, you'll notice in the previous questions I didn't say anything about the other thing. So we kind of assumed the temperature was constant, or we assumed that pressure was constant, and now we're kind of assuming that the volume is constant, although if it says metal container, it's a pretty good indication that it's not going to be changing until the lid flies off. So I have a pressure, and I have a temperature, and I have a new pressure that I'm trying to figure out, and a new temperature. Now, one nice thing about negative temperatures is if you use them accidentally, use the Celsius temperature, and you get a negative answer, there should be a couple of alarm bells that go off. But you still, either way, cannot use Celsius temperatures. You'll be given those all the time, but you can't use them. This is what I'm using, Guy-Lussac, the pressure temperature law, and converting my temperatures. So if you have these and you're doing them, here are my answers for that. Now, a couple quick little things. I may have rounded off more than you. I may have rounded off less than you. But if we're in the same neighborhood, then we're all set to go. You might be wondering, what if all 3, volume, pressure, temperature, what if all 3 happen to be changing? That's going to be something called the combined gas law, where we take those 3 smaller ones and we combine them. We'll talk about that in class. What happens if I'm not changing conditions, but I want to know more information about it? What if I simply have a gas at 2 liters and 40 kilopascals and 600 degrees Celsius? What about that? Can I know more information about that if I'm not changing conditions? Yep, and that'll come up in another video. So there's more that we can do with gases, but as our starting point, here's where we go. Anyhow, talk to you in class. We'll give you some more questions, and we'll talk about the combined gas law and things like that. And then we'll just do some more math with it. Talk to you later.